Okay. So since we have the exam on Monday, today is just a review day. It's recapping chapters 1 through 4 because that is what will be on the exam. I also want to mention before I forget, chapter 4 homework is due tonight, so be sure to get that done and otherwise just be reviewing for the exam. So the plan is I'm going to recap what I think are the most important bits of each chapter. That doesn't necessarily mean that's all that will show up, but they will be a focus of the chapter. Um, Aside from that, once I get through that for each chapter, it's really just whatever questions everyone has. So be thinking of questions, be looking at that review packet thing. It's really last semester's exam that's up on Canvas. And if you have questions about any of those questions or anything else, be thinking about those so we can answer them after I get through the recap. Okay. Um, Exam logistics. It'll be same time, same place on Monday. No calculator is needed. You can bring one if you want. There's no problem with that, but I don't think you will need it. There's no cheat sheets or anything because on the exam itself, it'll look pretty much exactly like this. It will have any of the equations we've used previously, and otherwise it's just conceptual questions. All right. It'll be 40 questions, but people typically finish in 15, 20 minutes a lot of the time. So time is usually not a big issue in this. Okay. Going through, we were kind of setting the stage for what we were going to do in the class for most of chapter 1. So the main focus really starts here. Facts, hypotheses, and theories, and most importantly, telling when a hypothesis is scientific. So there needs to be a test that could, in principle, prove that hypothesis wrong, because if you can prove it wrong, you've definitively shown that there is something wrong with that hypothesis and that you need to update and improve it. If you've just shown in whatever experiment you did that it didn't fail, that means you just showed that it didn't fail for that experiment. That's helpful information, but it's not as far reaching as a hypothesis coming out wrong. So we're not at the end of the day trying to prove hypotheses wrong all the time. That's just the way in which we approach them so that we can get very strong hypotheses that we've tested a lot of times and haven't been able to prove wrong just yet. So expect a lot of questions like, let's see, these of is the statement that's given scientific or not scientific? And maybe these, but this was where we had to be really careful and think about the distinction between these two, and that's trickier. So I'm more focused on the ones where it just gives you a statement, says, is it scientific or is it not? And I'm sorry if you're hearing the neighbors' dogs. They're having a good time out there today. After that, the stuff on finding the size of the Earth is not on there. It's just an interesting thing that was done by early scientists. So really, we're already into chapter 2. Because Aristotle's views of motion we now know are not correct, they're not a big focus. I think that would be not the best way to go about things. But Galileo's experiments are a big focus. So, what did he figure out by going up to the top of the Leaning Tower of Pisa? That things fall at the same rate regardless of their mass. We know air resistance is the only factor, and we know exactly how it plays in now, but that is not on this exam. Non-free fall, air resistance, all that stuff at the end of chapter 4 is on exam 2. Okay, from inclined planes, we want to know what he found out. And it was this law of inertia that if nothing is changing how an object moves, like friction, it will keep moving the way it was. And that was refined into Newton's first law of motion. So Newton's first law tells us about inertia, this property, that matter likes to keep moving the way it's moving, whether that means just sitting there because that's what it was doing, or moving in a straight line at constant speed. And that is what Newton's first law says in more flowery language. Being able to find a net force is something that I don't think is too difficult. I think you'll do well at that, but it is something that will be asked about. So if you're given two forces, can you find the net force? Primarily in these cases of the forces being along the same line, forces being perpendicular or at some other angle like this are not a focus on the exam. Equilibrium is a very important one, and it says several things. It says the net force on an object is zero. It says the object is not accelerating. It says that an object moves at straight line or at constant speed in a straight line or remains at rest. Either is a case of equilibrium. So those are more or less equivalent statements. So what equilibrium is when zero net force acts, but the consequences of that are that something either remains at rest or keeps moving in a straight line at constant speed. The only calculation type problems that show up from this are you're given some forces and you got to find some you don't know anything about. So a problem similar to these three that we did is likely to show up. So you'd be given some forces and you just got to figure out the unknown one by using this law of equilibrium, that all the upward forces have to be balanced by downward forces of the same overall size. As we go on, support force is what is measured by a scale. Scales measure support force, not weight. And the only reason that the number happens to be the same as what we think of as our weight is because we are in equilibrium most of the time when we're standing on a scale. But if for whatever reason we're accelerating, we jump on the scale or even just quickly squat down or stand up, that is not true, and the scale reading changes even though our weight does not change. Knowing that both static and dynamic equilibrium are possibilities, meaning static equilibrium is something at rest, dynamic is something moving straight line at constant speed. And we looked at kind of how those can each happen. As far as, I think, numerical questions, ones like this, where you're told that something's sliding at a constant speed in a straight line, you can infer that the net force is zero, and that would mean that if you're given one force, the other force has to balance it out. And one kind of like these of because of inertia, because the coin keeps moving with the same horizontal speed it had when it left your hand, it lands back in your hand unless you speed up, slow down, or change direction. So still just inertia stuff. For chapter 3, let's see. Speed is really the first thing we start with because we come back to relative motion at the end, so I'll save that for the end. So the difference between average and instantaneous speed, I would not say is heavily stressed, but just having a sense of what speed is, and really more importantly, how it compares to velocity. So speed is the number, velocity is the number and the direction. So they are different things, and that can mean that you could have a constant speed, but not a constant velocity if it's that you were always driving at 50 miles per hour, but part of the time you're driving east and part of the time you were driving west. Okay, acceleration, knowing what it means, is telling you something about how your velocity is changing. That could mean either you're speeding up or slowing down, or it could mean you're changing direction, or all of the above. So all three things are accelerations. And that means if you see a question where it's like, which of the following is not an example of acceleration, do not choose taking a turn around a corner because that is an acceleration. Even if it's a constant speed, your direction is changing, and so your velocity is changing. Constant acceleration means that your velocity is changing by the same amount each second. So that's what all these were about. that you speed up by 1 meter per second each second, that is a constant acceleration of 1 meter per second or 1 meter per second squared. If your velocity is increasing by 4 meters per second each second, that's an acceleration of 4 meters per second squared. Free fall, questions involving this idea of that your velocity changes by about 10 each second. So if I throw a ball upward at 30 meters per second, how long does it take to reach the top of its path? That one's not rhetorical.
Is it 10 minutes per second?
It's 10 meters per second each second. So if I throw a ball at 30 meters per second, how long does it take to reach the top?
3 seconds.
Mm-hmm. Because you see that each second that passes, 10 meters per second of that velocity is shaved off. So you go from 30 to 20, and then to 10, and then to 0. That takes 3 seconds, and what is special about the top of the path is that the ball is, or whatever the thing that's thrown is momentarily stopping at the top. Okay, if I throw it at 20 meters per second, how fast and which way is it going 5 seconds later?
It's going down 30 meters per second.
Yes. Yep, exactly. So you can count that off all the way up to 5. You say you go from 20 to 10, that takes 1 second. 10 to 0 is 2 seconds. And then 3 additional seconds pass for you to go from 0 to 30 meters per second, but the other way. So that would be like if the ball actually started here, and then let me zoom in on that. And then 1 second passed, you're here. Another second passes, it stops. Another one, and one more second. That's 5 seconds overall. So if questions like that are straightforward, you'll be fine on this section. There might be one distance question, and that's really just this formula, which you're given on the exam. So it's just remembering that that's where you go to find how far something has fallen if it is in free fall. Hang time is not on there. Okay. For relative velocity, if I tell you that someone's going 5 meters per second one way relative to the floor of a bus or some other moving thing, but that moving thing is going 4 meters per second the other way, could you tell me their velocity relative to the ground? So bus goes 5 meters per second to the right, you run at 4 meters per second to the left, or no, sorry, you run 5 meters per second to the right, bus goes 4 meters per second to the left. How fast are you moving relative to the ground?
45 meters to the right.
Would be, say that again?
Is it 45 meters to the right?
No, it would be, so the comment I saw in chat was 1 meter per second. It would be 1 meter per second to the right. So reason being, we'll just think of a moving platform. It's moving 4 meters per second this way. You're running 5 meters per second this way. Someone watching all this happen from the ground is only going to see you move 1 meter to the right each second. Because for each 5 meters you move to the right, the thing you're on has moved back by 4 meters. You're only getting a net gain of 1 meter to the right each second. So your speed relative to the ground would be 1 meter per second. And velocity relative to the ground would be 1 meter per second to the right. So questions like that are what can be expected for relative velocity. Chapter 4, Newton's second law and friction. So I'm going to come back up in a second, but a lot of this was just building up to what Newton's second law says. So let's look at it first. It says that if you have more net force on something, its acceleration increases. If it has more mass, its acceleration decreases. And the overall acceleration is kind of an interplay between those two things. Net force increasing tends to increase it. Mass increasing tends to decrease it. If both change by the same amount, you can expect that the acceleration does not change. So problems like these are definitely to be expected. Being able to just get a sense of what happens to the acceleration when you do something to the net force, something to the mass. You can do it this way, where you choose values for stuff and see what happens when you change one of those values. Or you can just think about it as, if I increase net force, I know acceleration should increase. So that knocks out usually half the answer choices because they talk about the acceleration decreasing. And then it's just up to you to realize that specifically if you double net force, you double acceleration. If you triple net force, you triple acceleration. And similar for mass. If you double mass, you halve the acceleration. If you triple it, you bring the acceleration down to 1/3 of what it was. Okay, now I'll come back up to friction. So friction has two types. There is static and kinetic. Static is when stuff is not sliding across other stuff just yet, but it's trying to. Kinetic is when the stuff is sliding across something else. So, friction only happens when you are trying to get something to move horizontally. So it doesn't happen if you've got something just sitting on a table. But if you try and push that thing, even if it's not moving just yet, it does have friction acting on it, and that would be static friction. Once it does start moving, you then have kinetic friction acting on it, and that's making it a little bit harder for you to accelerate it. It's resisting that acceleration by acting in the opposite direction of sliding. So let's see the difference between those and how they differ from each other. I just said the same thing twice, didn't I? Difference between static and sliding, and then what their properties are, so that static gets stronger as you push harder. Questions like these are still equilibrium or Newton's second law, depending on if a force is winning or if they're in balance with each other. So those are good questions to review. The difference between mass and weight, primarily in the sense of that weight can change, but mass does not. If you go somewhere else, you can change mass by cutting something in half or burning it or doing something to physically change how much stuff is in it, but not just by taking it to a different place like you can with weight. These are not on there. I just wanted you to see live and in person that there is a real world difference between mass and weight. I would say this kind of is a little bit intricate, how you're moving versus which way the force is acting and what that says about how your motion changes. We won't really have much of that yet. As we see more of like rotational motion and other things, we'll look at that more, but not right now. So last thing is free fall, but the force side of it. So why things all have the same acceleration. It's because when you increase the mass of something, you're not only increasing the gravitational force on it, because you are increasing its weight. You're increasing the pull of gravity when you increase something's mass. But you're also increasing its inertia, which would be its resistance to acceleration. So you're increasing both the force and the mass by the same amount. That leads to no change in acceleration, which is why we always get the same acceleration, no matter what the mass is. So questions like this one. But knowing that increasing mass absolutely does increase the force of gravity on that object. It just so happens that it also increases the inertia of the object, and those two effects cancel out to give the same acceleration. Okay, and again, that is it for exam 1. So all of the stuff past that is not on the exam. It will be on exam 2. All right, that is my recap. Now it is open to whatever questions y'all have about anything.
How do you calculate, like for the chapter one, the if you throw a ball up and then it goes back down, how do you calculate that again?
Sure. So that I think is chapter 3. Yeah, this right here. So how you do it is just in your head, think about usually you'll be given an initial speed, maybe 40 meters per second or some other number. If you're asked how fast it's going a certain number of seconds later, you can do it two different ways. They're equivalent to each other, but maybe one's easier to kind of think about than the other. So say I get asked about 9 seconds later. I'm just pulling a number and saying, you could do this with any number. You could either, if you're more algebra minded, use that equation. And it's saying that for each second that passes, t is time, you multiply by 10 and you subtract that off of 40 because the gravitational acceleration changes the acceleration of an object by 10 meters per second each second. So for this 9-second time, that would be minus 10 times 9 seconds. 40 minus 90 is negative 50. That negative just tells me that this thing is going downward instead of upward. So after 9 seconds, it is going 50 meters per second downward. That's one way. The other way is count off the seconds one by one and think about this a little bit more physically. So after 1 second has passed, how fast is this ball going upward? Because it would still be going upward after 1 second.
Be 30.
So 30, that's after 1 second. After 2 seconds, it'll be going
20.
20. Okay. After 3 seconds, it's going 10. And then after 4 seconds, it's going 0, which tells us we're at the top. Because when it reaches 0, it stops for a moment and then turns around. So we've gotten through 4 of our 9 seconds. We've got 5 seconds left. That means it's going to start increasing in speed as we go back down. It'll be 10, 20, 30, 40, and then finally 50 meters per second, because that would be seconds 5, 6, 7, 8, and 9. So we still get the same answer, and we still realize it's falling downwards. Does
Thank
that
you.
answer? Yes. Okay. Other questions?
A quick question. When it's at 0 meters per second, is that like the 5 second mark, right?
It would be after 4 seconds for this one, because it was originally going 40, and it took 1, 2, 3, 4 to get to that 0 meter per second height.
So for like this example, at 5 meters per second, it's at 0.
After 4 seconds,
Second.
it's at 0. So the
Oh, okay.
stopwatch would say 4 seconds. Yeah.
Okay, thank you.
At 5 seconds, it would be falling at 10 meters per second downward. And the algebra way to solve those types of problems where it's asking you how long does it take to reach the top is you can count it off like this and see how many seconds it takes to get to 0, or you say 40 minus 10t equals 0 and you solve for t, and that'll still give you 4 seconds. Okay, other questions? So we do have the practice exam as well. So y'all can look through that. And if you have any questions about specific problems and why the answer is what it is, we can do that. All right, maybe I'll just pick a couple. While I'm doing that, be thinking of some questions because I my bit I've done. I'm happy to answer anything though. So let's see. Let's maybe look at a couple from each chapter. So what about this one? The statement no two snowflakes are alike is, what do you think? Testable or non-testable?
I feel like that
Testable.
one's tricky because, like, isn't that a known fact? But then how did they test that? I don't know.
Yeah. So that's a good point. And when we're answering these types of questions, we have to forget about what it is that we know because it plays no role in whether the hypothesis is scientific because how did we figure out in the first place? We had to come up with a testable hypothesis. So always kind of throw out whether you know it to be true or not. That doesn't matter. And something being true or not does not make it scientific.
Is this
So
one like the alien one where it's a lot easier to test, I guess, for life than no life? And that one's like, because you'd have to test every single snowflake.
let's let's break it down into
Okay.
steps. So the first step would be we have to see what it would mean for it to be wrong, and then we can kind of decide if that's something we can accomplish. So what would it mean if this were wrong?
They're all snowflakes are alike.
So this says that no snowflakes are alike. That it would be wrong would be that there are at least two snowflakes that are different. It's probably the wording of it too. It's a weird way of saying all snowflakes are different from each other. But how we would disprove that is I find snowflakes that are the same. Maybe I said previously different, I'm not sure. So if we can find two snowflakes that are the same, then we're good. This is a testable thing. We can look for snowflakes until we find two that are the same. And that's not exactly like the alien thing because it doesn't require us to check every snowflake in existence just by
Yeah, that
default.
one's
Yeah.
the one that is like the one that's testable, I guess. Yeah.
Yeah.
Like you said, when you break it down, it's much easier, but when you're just reading it, you're like, what?
I
This is a
100%
negative.
agree. I have to do this when I do these questions because
Yeah.
otherwise, if to me it is that confusing as well.
Yes.
So it would be testable. This is something I could reasonably do, and it is something people reasonably did and found out that you can have snowflakes that are the same, but they aren't. There are many different varieties of snowflakes that you can get. Okay. What about this one? Research done in the physics department is the best research done on campus.
Non-testable
Yep, that's an
because it's an
opinion.
opinion.
Yep.
Yeah.
I don't care how positive a light it shines on us. If it's an opinion, it's not testable. Um, there are things we will never know.
Non-testable.
Non-testable. Anything like that, where it's this almost intentionally vague thing, like matter is filled with undetectable particles. It's like in the wording, it's built in that you can't figure it out. You can guarantee it's non-testable because there is no test to figure out something that cannot be tested. Um, okay, pre-med students with degrees in physics will always get into medical school.
I feel like that's testable.
It is, and that can be a little tricky. So what would it mean for it to be wrong?
if a biology student got into med school?
So that wouldn't mean necessarily that pre-med students don't always get into med school. Are you distinguishing between biology and pre-med, or saying a biology student is a pre-med student? That factors in as well.
To be honest, I'm not sure. I think I might have read the question wrong.
Okay, that's okay. So it would be, I saw in the chat, one student that doesn't get into medical school that was in pre. So yeah, a pre-med student with a degree in physics. Or I guess we need to find a pre-med student with a degree in physics that did not get into medical school. That's how we would prove this wrong. And even if that person doesn't exist, even if we really do look through everyone and find that really every pre-med student with a degree in physics actually does get into med school, I don't feel like that's true, but if it was, this is still something we could do, and it's not unreasonable at the outset. So I could look around, I could ask around, look for pre-med students that had physics degrees, ask if they got into med school, and it doesn't require me to ask every single pre-med student who's ever gotten a degree in physics in order to do this test. So it would be testable. Okay. There are regions beneath Earth's crust that'll always be beyond the reach of scientific investigation. We never really used the word speculation, but that would be the word for statements like that. It's something that people can state and guess about, but it's not in any way testable because of this, like, intentionally, we'll never know. If you phrase it like that, then you've like set it up to not be testable. Okay, that's the main ones for chapter 1. So are there questions at this point? Otherwise, I'll look at some chapter 2 stuff. Okay. All right. When you're in the aisle of a bus and the driver takes a left turn, why do you shift to the right? Without looking at the answer choices, just tell me what you're feeling.
Your body wants to keep going straight.
Yep. And what do we call that property?
Inertia.
Mm-hmm. So it's choice D. We just want to rule out that it's really friction is maybe the only other one that you would kind of worry about because the other two pull you downward, not to the right. So it's not friction because that's actually what lets you take the turn, is what changes your motion in order to go around that left turn with the bus. So it is your inertia. All right, I think net force is usually fine. If no external net force acts on a moving object, what will it do? So what does this tell us about the object?
It is at rest.
Yep. I guess that just crashed. 1 second. Or it is at rest, or there's another option.
It's moving at constant speed.
In a straight line. So it will continue moving at the same speed it was going at in a straight line. That's not stated there, but that is true as well, in a straight line. Okay, let me ask this. You've got a force acting on something. It's a rock or something else, and it's let's see, 30 newtons. Just give it some number. So the rock will accelerate as a result of that force. Now we have a force in the opposite direction of the same size. What does the rock do after that? So suddenly that second force adds on. What does the rock do?
The
Yes,
rock would
Lineation.
Take a shit.
I'm sorry, that was an accident.
Oh, okay. All right. I think that was Tierra then that was saying something. I'm sorry.
The rock would consistently keep going in a straight line floating.
Yes, that's exactly it. And Cameron, you got it too. So I think a common thing I see is you see this and you almost see it like running into some, I don't know, rumble strips on the road or something. Like it suddenly just slows you to a stop, or it's like hitting a brick wall. No, it would be if you had a very large force in the other direction, but this is the same size, and so the rock doesn't accelerate anymore. It just keeps moving at the speed it was moving at as soon as this force turned on. So, yep, you guys are right. Okay. What is always true of an object at equilibrium? Number 18.
All of the above.
Read through them again and see if you still think so.
Would it be acceleration is zero?
Okay. So,
Hmm.
I'm going to put a pin in that for just a second.
Okay.
So, velocity is zero. Is that always true for something in equilibrium?
No.
No, because we were just talking about that it can also keep moving at the same speed in a straight line. No net force on it is equilibrium, right? So these questions are different variations on the same thing. It just words it in slightly different ways to try and trip you up. So velocity is zero is not always true because something can also move with a constant speed in a straight line. And that means D is wrong as well because clearly it's not all of them that are true. And that means I also need to throw out either one of A or B. So B, no forces whatsoever act on the object. Is that the only way you can have equilibrium?
No, because you can have equal forces, right?
Yeah, as long as they're balancing each other, equilibrium, that is what matters. You can have 1,000 forces acting on something, but if they add up to zero net force, they all cancel each other out, then it is still in equilibrium. So that one's out, and you were correct. The acceleration is zero. That's the only one that is definitely true, because that could either mean it's not moving at all, or its motion is just not changing. It's not speeding up, slowing down, or changing direction. Okay. So, which one does not describe something in equilibrium?
D.
D.
Okay, D, yeah, it is that one because
Did
in that,
the velocity change?
yes, absolutely it is. So car rounds a curve. That means velocity changes because the direction changes. That means acceleration occurred. Which means a non-zero net force acted. There was an imbalance of forces to change the car's motion. And in particular, it would be friction from the road that is acting towards the center of that turn. We'll talk about centripetal force later, but that is an example of a centripetal force. Hockey puck moves uniformly in a straight line. That should probably say at 1 meter per second. In a straight line, that is equilibrium. That's constant velocity, no change in the motion. Box sits on the floor. That's static equilibrium. A was dynamic equilibrium. B is static equilibrium. C is dynamic equilibrium because the forces are balancing each other out. So the net force is 0, so it will move at a constant speed in a straight line. All right, good. Okay. If something moves with constant acceleration, what's true about its velocity?
B.
Yes, that is it. So constant acceleration doesn't mean zero acceleration. That's usually the misconception. It means that the number is a fixed number, 1 meter per second, or 10 meters per second for gravity. So it's just saying the velocity is increasing or decreasing or whatever it's doing by that amount every second, rather than a non-constant acceleration would be it was the thing sped up by 1 meter per second in the first second, but 5 in the second, and then 10 meters per second in the third. And that would be like you're changing how hard you're pressing on your gas pedal so that your acceleration, your kind of get up and go, is changing as you drive. I don't know if I ever mentioned this, but the rate of change of acceleration has a name too, and it's called jerk. And then the rate of change of that is called snap, and then crackle, and then pop, and then lock, and then drop. Those are all real terms. They don't get used a lot, but they are real physics terms. Okay. This one's a little tricky. Bullet is dropped into a river from a high bridge at the same time another bullet is fired straight down from a rifle. How do their accelerations compare as they're about to hit the water?
B.
Which one?
B.
B.
B? Okay, and B. All right. Like I said, this one's tricky. The answer is C.
Oh no.
So let me walk you through this because, again, it is tricky. So these will be our bullet, and this is our rifle firing another bullet. Let's say it fires it at, I don't know, 200 meters per second. This one is dropped, so it's initially 0 meters per second. Once that bullet has left the rifle, is the rifle pushing on it anymore?
No.
So what forces are acting on that bullet?
Gravity.
Just gravity. And so that's the only thing that determines its acceleration. The net force is the force due to gravity. And so its acceleration will be free fall acceleration. That'll mean after 1 second, it's going 210 meters per second. And then 220. And then 230, and however fast it ends up being when it hits the water. So its velocity is going to be huge compared to the drop bullet. But the change in velocity we're seeing between any two times will also be 10 meters per second per second. So this
So it
one,
would be like a constant change. So is that what you're saying?
it would be, yeah, the change in velocity is the same over each second. That would be what you would call a constant acceleration.
Okay, yeah, that's what I was.
Yep. And that's what constant acceleration almost feels like a contradiction. But it's just saying that the number describing that acceleration is a fixed number. So this one also has the same acceleration, even though its velocity, how fast it's going when it hits the water, is very different. It's also true if you throw something down at the water. It will still have free fall acceleration once it leaves your hand, but it will hit the water faster.
So what would be an example of like when that wouldn't be true? Because like gravity's were acting upon. Okay, I don't know. Do you know what I'm saying? Like an
I
opposite
think so.
example? Okay.
Yeah. So one example would be if you don't have this this bullet just freely falling, like not connected to anything.
Okay.
That would be, I don't know, you've got some it's attached to a really long spring, for instance. Like it's a toy gun and it doesn't release the bullet. It's like one of those like cartoon guns where it just has a little bang
Okay,
sign
that's
on it,
pretty
you know?
cool. Yeah.
Yeah. So it would have not only the force of gravity pulling it down, but also the force from the spring pushing on it.
Right,
And
because
that's
it's
going, Mhm.
connected. Okay.
Yep. And actually, air resistance, drag is an example that is different because you end up with that extra force upward, and that would reduce the acceleration down from 10.
Okay.
Yep.
Very cool.
All right, let's see. A rock is thrown upward, which is not 0 at the top of the path. Which one do you know for sure is 0?
Speed and acceleration.
Speed is 0. I agree with that. I wouldn't agree with acceleration. Okay. So we think about, I would agree that it is the correct answer, but I wouldn't agree that it is 0, I guess is what I'm trying to say. So you throw something upward, it rises, it rises. What's special about when it reaches the top?
You did something on a graph or like that showed this. I just don't remember.
Well, let's say I threw it at 30 meters per second. 1 second later is 20 meters per second. 1 second later is 10 meters per second. What's special up at the top?
The top one, it goes back to 0.
It's 0. What is 0 specifically?
The speed,
The speed
oh,
and how,
the
what, yeah, go
velocity
ahead. Yeah,
and the
velocity.
velocity.
Uh-huh. Because velocity is just speed with direction. So if the speed is all gone, the velocity is all gone. But the acceleration tells you how that's changing from 1 second to the next. And so that is still happening as we go from when the ball is going at 10 meters per second to when it's 0 meters per second. That is still a change of 10 meters per second per second. And then as it falls back down, it is now going to be going 10 meters per second the other way. That's still a change of 10 meters per second happening, even at the top of the path. So the acceleration is never 0. It's always 10 or 9.8 meters per second per second. And that would mean it's the one thing that is not equal to 0. That one is hard. I mean, every level of physics, that is a question that a lot of people mix up things on because acceleration is not as intuitive a concept as velocity or speed. Okay. Crate sits on a floor. Friction between the crate and the floor occurs when what happens? Let's see. Only if the crate is sliding. So, crate sliding. I agree there would be friction resisting that motion. But are you saying that when I push on it, but it's not moving yet, there's no friction?
Would it be C? Because you said earlier if it's even trying to like act on it.
Yeah. And the reason I know is if something's not moving, but I'm pushing on it, that thing is in equilibrium. It's at rest. So what must be true about the net force on it?
If it's in equilibrium,
Uh-huh.
0.
0. But I'm pushing on it. So I need something to balance that to get a net force of 0. That other thing is friction. And so it has to act in order for something to stay at rest while you're pushing on it, which we know is a thing that can happen, especially with a real heavy crate. If you're not pushing on it, that means there's no force this way from you, and so there doesn't need to be a counteracting force from friction to balance it. So the answer is C. When it's pushed, whether it has begun sliding or not, it is not even when no pushing occurs. That's this case where nothing's really happening of interest, and you don't have to push on the crate vertically in order for this to happen. And that has to do with, we've talked about components of a force. Only the horizontal component of your push actually matters for the friction. Okay. This one I think is a little bit vague. Whenever a net force acts on an object, there is a change in the object's. I think it's better to say must be, or there is always a change in. Which one of these?
Direction or velocity.
I'd say,
Maybe.
yeah. So it would be velocity because that's the one that's like all encompassing.
Yeah.
Yeah. It could be direction that changed for that velocity to change. It could be speed. It could even be shape when you talk about in physics, you call them deformable bodies. It's just stuff that can squeeze and squish and all that and change shape. But the overarching thing that changes is velocity. All right. If mass is doubled while the net force is also doubled, what happens to acceleration?
Does the acceleration doubles as well?
So it sounds like you're
Doesn't
thinking
it
about,
have? Oh, sorry.
I want you to both tell me why you're thinking what you're thinking, because I agree a little bit with both of you.
Because if everything else is doubling, wouldn't the acceleration double with it so that you get the number that you're looking for?
Well, what does increasing mass do to acceleration?
It decreases
It
the
decreases it.
acceleration.
But increasing net force does increase acceleration. So we've got competing things happening here. In fact, they exactly cancel each other out so that the acceleration doesn't change. If we want to do that with kind of a more mathy way, using Newton's second law, this is net force up top and then mass on bottom. I can say, pretend the net force was originally 1 Newton. The mass was originally 1 kilogram. And again, you don't have to remember the units to do this. You can just write 1. But we're saying the mass is doubled. So the mass becomes 2 kilograms. And the net force is doubled. So it becomes 2 newtons. How do the accelerations compare in each of these cases?
One was increasing, one was decreasing.
Yeah, so in this first case where I had a 1 Newton force on a 1 kilogram mass, I had an acceleration of 1. Again, units don't matter, but it would be meters per second squared. My acceleration in the second case would be 2 newtons acting on 2 kilograms. What's that equal?
1.
Again, 1. So my acceleration did not change between these two cases because of competing things happening. The push, the thing making the block move, increased, but so did the resistance to that push, the inertia of the block. And those two things fight each other, and it ends up being a stalemate. Nothing changes. The acceleration is exactly the same. But let's go back to this simpler example now. If the net force acting on a sliding block is somehow doubled, what happens to the acceleration in that case?
Would that remain the same?
So now mass hasn't changed, but just the net force has. What do you expect that'll do to the acceleration? You don't have to give a number, but just how would the acceleration change? Get
It
bigger?
would increase.
It would increase. So the difference between these two questions is that both things changed in 35. Only one thing changed in 34.
Okay, that makes
Yep.
a lot.
And we could again go through this math. We would see really just this part of it happen. The mass would stay 1 kilogram. And so if you compare the accelerations, it would have originally been 1, and then it becomes not 1 again, but 2. So the acceleration is doubled. But like I said, the easiest way to approach this is sometimes just to say, if net force increased, I expect acceleration to increase. That automatically knocks out this one. And if I remember that if mass isn't changing, that I don't have to worry about that bit, this one's knocked out. I'm down to these two. And then I just have to remember that it's always however one changes, the other changes in the same way. So since the force doubled, acceleration doubles rather than quadrupling. Okay, we are out of time, but if there are additional questions, even over the weekend, please email me. I'm happy to answer them. Chapter 4 homework is due tonight. And otherwise, I'll see you all on Monday, hopefully in a smell-free building. I don't know if you all were there when it happened, but it was pretty intense by the end of the day. So anyway, enjoy your weekend.
Have a great one.
Thanks.
Bye.
Okay, I still see Brandon, Krista, Haley, Jamie, no, not Jamie anymore, Michaela, and Manuel. Did any of you have any questions? Okay, well, if no more questions, I'll end the call.